All right, in section 6.5, we are going to start looking at sampling distributions and the central limit theorem. So our big picture for this section is how is the sample statistic, which is x bar, our mean, excuse me, how is that distributed, okay? So this leads us actually to a few different things that will be important throughout the rest of the course. So one of them is to talk about what statistical inference means. Okay, statistical inference is making accurate decisions about parameters. And remember, parameters apply to the population. Okay. Based on statistics, which again, the statistics come from the samples. Okay, so we're trying to make accurate decisions about the population parameters, so means, proportions, etc., based on statistics, smaller samples from within the population. Okay, so accurate is really something we want to be able to measure. How accurate are we really being? Okay, that accuracy will be done using probability. Okay, now when we had binomial and normal distributions, we knew what distribution the variable followed. We knew it was binomial or we knew it was normal. But the real question that we're going to be looking at in this section is what happens when we don't know anything at all about how the variable is distributed. Okay, if that is the case, then we need to know the shape of the statistic. In this particular section, our statistic is going to be the sample mean. Okay, so what we're going to look at is called the sampling distribution of sample means. So what does this mean? Okay, well, this means that we take many samples, many, okay, take many samples of size n from the population, find the mean of each sample, and then graph the sample means. All right, so you take many samples of size n, say 50 people, okay? Let's say you want to find the height of, I don't know, adults in this country or whatever. So you would take many, I mean like thousands, okay? Thousands of samples of size, say 50 from the population. Find the average height of every single one of those 1,000 samples and then find the mean, okay? So now you have 1,000 different means and you graph the sample means, okay? That's what we're looking at doing here. All right, so when is it that our sampling distribution of these sample means, so all of these distributions of all of these means that we found, when will they be normally distributed? This question is answered by the central limit theorem. So if the population is normally distributed, so if you know the population, so if you know heights, for example, are normally distributed already, okay, we have that information, then the sampling distribution of sample means will also be normally distributed. So normal gives normal, okay, no matter how many are in the sample, whether you did groups of 10, groups of 50, groups of whatever, okay, the sample means will also be normally distributed. However, if the population is not normally distributed, or if we don't know, okay, maybe we just don't know, like we're looking at maybe the SAT scores of students who got into like Ivy League schools, for example. We may not know that distribution or we can't find it out, okay? Or maybe it's not normally distributed at all. In that case, actually, it's probably very much skewed to the right. skewed to the left, very few low scores, lots and lots of high scores, then the sampling distribution of sample means will only be normal or be normally distributed if n, the sample size, is greater than or equal to 30. Okay? In other words, you need samples that are large enough. And if you have samples that are large enough, repeated samples over and over and over again, then the sampling distribution of all of those means, all of those averages together, will be normally distributed. Okay, so how would you calculate the mean and standard deviation of a sampling distribution of sample means? And this is part of the central limit theorem, like continued on. Okay, this is not new, it just doesn't all fit on the same page. So the mean of x bar, okay, so what this is the mean of the sampling distribution. That's the notation that we're going to use, okay, is the same as mu, the mean of the population. And furthermore, the standard deviation of x bar, so the standard deviation of your sampling distribution, is going to equal sigma over root n, which is the standard deviation of the population divided by the square root of the sample size. Okay, in case you don't remember what those notations mean. That part right there, this, okay, is called the sampling error. So you'll also see that term periodically, okay? That standard deviation of your sampling distribution is known as sampling error. A couple of things to note. As n increases, so as n gets bigger, as this number right there gets bigger and bigger and bigger and bigger, the standard deviation gets smaller, okay? It decreases because you're dividing by a bigger and bigger and bigger number. So as you divide by a bigger number, your standard deviation gets smaller. In other words, your error gets smaller as your sample size gets bigger, okay? In our notation, so it's going to be that x bar, the sample means, are normally distributed with a mean equal to, again, the mean of the population, and then our standard deviation adjusted for the sample size. So another way to look at that is it's normal with the mean equal to the population mean and the standard deviation equal to sigma over root n.